Welcome to Homework Lib.
In problem 42.26, we're told that pure germanium has a band gap of 0.67 eV. So what this means is if we have our germanium here, the gap between the conduction band and the valence band is 0.67 eV. And also, we are told that the Fermi energy lies in the middle of that gap. So that's our EF there. So in terms of what this problem is asking, first we want to look at several different temperatures and calculate the probability using the Fermi distribution function for a state at the bottom of the conduction band being occupied. So that's that there's things filled up at the very top here. To walk through what that means for something up here to be occupied, that means that if we define our band gap as delta E equals 0.67 eV, we want to find the probability that we're going to find states being occupied at an energy E equal Fermi energy plus delta V, or delta E, sorry, over 2. Because this distance is the only frame of reference we have. Because you notice it doesn't give you an absolute energy, just a Fermi energy. And that's vital because otherwise our Fermi distribution function here is useless without something to put in for E. But we have something, so if we take our Fermi distribution function and plug in for our bottom of the convalence band energy, then that is equal to 1 over E, and then we have EF plus delta E over 2 minus EF, and that's all divided by KT. Now this KT we're going to leave general because we want an equation that we can just plug in all the different temperatures for. So we'll leave it in here for now. But you can see that these Fermi energies are going to cancel because you add one here and subtract one there. Thus, your Fermi distribution, we'll just say E here, is 1 over E to the delta E divided by 2KT plus 1. And that's perfect because you can just plug these into your calculator for all the different temperatures. So save a little time here. I'll just write them out. So for temperature equals 250 Kelvin, you get a probability of 1.8. Sorry, I'll use the notation that's used in the book. 1.8 times 10 to the minus 7th power. And for T equals 300, you get 2.4 times 10 to the minus 6 power. And then finally, for 350, you get 1.5 times 10 to the minus 5 power. And it's always good to stop and see if this is what you expect, which in this case it is, since as we increase in energy or increase in temperature, this S curve will start to spread out a little bit like this. So this would be a very high temperature, but leading to a higher probability of finding electrons over here in the bottom of the conduction band. So this is all well and good. This is our answer for part A. However, part B, which I'm going to start a new page for here, asks us to calculate the probability that we have unoccupied states at the top of the valence band. So here's the valence band. Here's an occupied state. Here's an unoccupied state. But the trick here is that whenever you have a state that is occupied at the bottom of the conduction band, that's the same exact thing as having an unoccupied state at the top of the valence band. So what that means is we can actually take our probabilities from before and run with them. It should be the exact same probability. Conversely, if you were asked the question of what's the probability that the top of the valence band is occupied, then in that case, it would be so like this. What you get in this situation is that it's actually 1 minus EF plus delta E over 2. So this relation is a handy little thing, but this is only the case for occupied states at the top of the valence band. But in our case, in the problem, it asks for that the states at the top of the valence band are empty, which are just the same probabilities that we calculated in part A, because for something to be empty here, it has to travel up there and be filled.